Hello? Hello! Wonderful.
Hello.
Okay, everybody. It's time for me to sit down amongst you and start to take in some of these sessions. This is where the day really kicks off, so I'm really looking forward to this. And so I will ask you, please put your hands together and welcome Sebastian from AI21 Labs.
Thank you, Mike.
Thank you.
Hello, everyone. Thank you so much for attending this session. I'm really always very excited to be in this area because I feel like this is the center of all of the activities. Thank you so much for taking time today to explore more on GenAI and really to take the time to hopefully also take a piece of idea or an advice with you and try it out. Looking forward to all the feedback after the session. So a little bit about me. I'm a builder by nature. I've gone through my career through being a developer, through a AI engineer, and in my past experience, I've always been intrigued by any technology that produces this kind of magical output. So I'm very excited to be a part of AI21 team, and I'm helping our customers take the models and the technologies that we build and implement them in most efficient way, and also solve some of the challenges maybe that before the recent family of models is available, these challenges were not really possible, not feasible in a commercial sense to solve. I live in Austin, Texas. Again, always very excited to be here. So this is a great opportunity for me to also learn. I had an opportunity to meet a couple folks. They're somewhere here in the audience right before the session, and I learned about how it was challenging 5 years ago to solve what we're doing today within minutes. So I'm hoping to help you understand how AI21 helps you with achieving your goals. So I'm going to talk a little bit about how we are building and architecting our specific model, but there are some components here that will probably apply to your other projects. And I'm going to talk a little bit about the architecture of the foundation model that we provide. I'm going to talk about our benchmarks, and I'm going to talk about how to best utilize it in the real world. So there are some specific use cases where you will see an advantage of using this model maybe versus another. When you start a project, you probably start with which tools do I pick for my project. Hopefully this will help you a little bit navigate the area of which model may be best for these use cases. So a little bit about why we have created our specific model. We're looking at the trade-offs. So when you look at implementing a new solution, new model, you often think about where is my benefit? Do I need something that's faster, that's of higher quality, or am I constrained by cost? And that was our driver as well. We saw the market and the current technologies kind of peaking at really good quality, but there was a bit of a gap in models that offered similar quality at lower cost, or even at the faster speed. So at inference time, the cost was rising. We're throwing more and more hardware at our models, and it was really challenging to find well-performing models at lower cost. And when I talk about cost, I'm really talking about memory here, which kind of translates for us, at least in a commercial sense. You're talking about how many GPUs do you need to deploy to achieve what you're looking for. I'm going to talk about our architecture of how we have created our Jamba models. This is the latest family. This is a model that we have released this year. Maybe if you've been to Bedrock, you've seen our models from the past. They're still there available. I'll focus specifically on this most recent model family because I think it has very, very nuanced advantages for the type of challenges we're seeing in today's marketplace. So just a bit of a step back. I think everyone is already familiar with the transformers. And really, they broke on the marketplace with their attention mechanism and how they're able, in a very complex situation, really understand the meaning of words. Obviously, the challenge with transformers is that as they are actually really good at what they do, they also have to take a look at a lot of data, a lot of tokens. So if you think about words, the challenge with this attention mechanism is when you process that information, you have to look at every single token against every other token. And this grows in a quadratic manner when you train. It used to grow the same with inference. Now we have some caching. optimize it, but it's still very, very expensive when you talk about large data sets. And large data sets, both for training and then for inference. When you have a large document that you have to process through these models, it's very expensive memory-wise. So you need a large multi-GPU cluster to be able to process these large data sets. But again, you really get the quality for it. So kind of this is where we see the transformer architecture. Great, great quality, undeniable. And now we're looking for solutions. Well, how can we also get the quality but increase our throughput and obviously the footprint of the memory, which translates to cost. So this is where we are looking at for our Jamba architecture. We saw a lot of customers coming back to us and saying, we have larger documents that even fit into this specific prompt. We would like to process those versus dividing those into multiple prompts and chunking those documents. So a year ago, a little bit over a year ago, Mamba architecture came out. Really, this is very, very recent. And when it came out, the team did a test, and it turned out that this was a very, very performant architecture. This is a throughput that you can see, and essentially, you can see how very quickly, as you increase the number of tokens, the amount of data that you send to a single GPU instance, you're getting very, very good performance. The blue line is Mamba. This architecture was performing really, really well. But it was originally tested with a very small sample, kind of fairly small model in today's terms. So it was still kind of unknown, would this really work in a commercial setting? In a commercial setting, we're talking about much larger models and much larger data sets. But it showed a lot of promise. And what we have done is we have essentially taken that model and we have used it to create an instance of that model. We have also taken what a Mamba architecture offers, which is it creates, instead of using an attention mechanism that looks at all of the tokens, it creates essentially a space. So think of it like a hidden space that you use, and you store some information in that space, but you only look at that space when you actually infer information. So instead of looking at everything, you only look at the very small subset of data, which again gives you an efficiency. You no longer require large amounts of memory to store larger documents. An example here is, when you think about this hidden state, think about when you look at a sentence, your input data, it goes into this hidden state, and then in a kind of a traditional model, you would essentially create a space that models every single part of that input. In this case, I want a hamburger. And instead of looking at all of the tokens, essentially, you look at just that hidden space. It's much more memory efficient. And what we have done is essentially we've taken this and the next version, so the team that has created Mamba has created a mechanism that makes that memory space a little bit more selective, so assigns weights to different words, to different tokens, to make sure that it's a lot more optimized. And in that mechanism, now we're getting very, very fast performance at inference time. We're getting much, much smaller memory footprint. And we're also getting essentially a much lower cost, much lower footprint to fit a very highly performing model. So this is kind of what it looks like right now with a selective model. We're picking which parts of the input are more important than others, and that helps us essentially achieve higher quality. So this is kind of what you can visualize with the trade-offs. You have transformer models, really, really good quality. Again, not hitting the marks on throughput or performance because of just how expensive it is with large volume of data. And then Mamba architecture, really good with high throughput use cases, but essentially not giving you the same quality. And the challenge here is, again, you want both. You want high quality, but you really need to do it at a commercially viable cost. So here's an example. So with the transformers model, you essentially, when you feed it, in this case, there's a sample prompt, we have a few shot, and we're asking the model to help us classify negative or positive sentiments, good, bad. And essentially, transformers are really good at this. The challenge is, as you scale and you send more and more input, it grows quadratically, linearly for inference time. So it gets very, very expensive very quick. So this is a small example, but imagine sending a 500-page document. It's essentially very, very memory intensive, but it's going to be very good about understanding that document. And here's what Mamba, like a pure Mamba model, does. It understands, because it has this attention mechanism, it knows the semantics, but it doesn't really understand the overall context. It doesn't really understand what the results should be. So it says, in this case, it just said it's bad, which is not the correct answer, but semantically it understands what we're asking about. So it has some good properties. And essentially, what we have done with Jamba is we have combined it. So we have transformer architecture that allows us to have very, very high quality. Again, the trade-off there is the cost and the speed. And we have the Mamba architecture, which now proves to be very, very efficient and doesn't require as much memory. So with Jamba, we have combined it. And as you can see, the layers are mixed. We have Mamba layers with transformer layers. We have additional technology I'm going to talk about in a second. But essentially, now we have kind of the best of both worlds. And it takes that engineering to figure out exactly where do we need to be with the balance and the trade-offs. But we're able to essentially get it to a state where now we're getting very high quality outputs with a much lower memory footprint. And that's really what we're striving for. So now kind of we're in this area of much higher speed, again, where we have some benchmarks to show for very high quality output, and also how we're managing memory. That's not the whole picture. We also had to take a look at, how do we increase both the speed and the quality of the outputs? And we're using a mixture of experts. So think of it as additional smaller networks that are part of the overall processing. And usually you will see that these experts are essentially really good at the specific domain. So an example may be you have a call center, and in a call center you have a dedicated teams for billing, teams for accounting, maybe customer returns. Essentially, an expert is really good at one specific thing. It's very focused on one area. So it really what it requires is it requires some type of routing, and essentially as part of the layers, you have routing mechanism that says which expert should I talk to, and the expert then takes over. You can think of like smaller networks within the overall set of layers. And by combining all of these components, now we have really high quality output and at much, much smaller memory footprint, and also a very comparable inference time that doesn't grow linearly. Actually, we have a really good benchmark that shows how it's almost a constant time inference. So this gives you kind of the model that has almost the best of both worlds. I'm going to talk a little bit about kind of where would you utilize that type of model. I have kind of a funny picture of like really what it looks like, right? We're taking parts of all the best parts, mixing those together, and we're getting this really, really efficient and very high-performing version of the model. So if you would like to use it, immediately you can use it on Amazon Bedrock. You can also use it on SageMaker. You can also deploy it on your own. It's available through Hugging Face. You can essentially take the model. We have open source versions of both. We have two versions. There's a mini and a large. The difference is there's the amount of compute you're going to need and the quality or the type of output that you will get. And all of those options are available. And what I would recommend as part of maybe kind of a follow-up is take a look at what's available on Bedrock as a starting point. What I always like to do is essentially try it out and exercise. In this case, what we're suggesting is exercise with large context. And that's really where we see the most benefit is if you have use cases where you have really, really large context or large amount of data you need to send, this is kind of where you would want to use the AI21 model, because that's where you can get both the efficiency as well as the memory footprint that's in a manageable format. Okay. So a few benchmarks to talk about. again, we're focusing on the speed and the memory as a kind of a cost factor. We wanted to make sure that when our customers were talking to us about increasing the size of an input, it was also in a manageable format where it wasn't growing exponentially their infrastructure costs. So we took a look at a couple different areas. One is just the overall number of parameters. And here you can see just our active parameters and the actual available parameters kind of in comparison to other models. What I really want to focus on is kind of the last column is the actual memory that we're using. So in our case, when you deploy these models, the memory footprint is maintaining really, really manageable volume. You can deploy this model on A100 CPU, GPU, and you can send 140,000 tokens into the model. So if you compare that to a transformer architecture, you will not obviously be able to deploy that type of sizable input on that architecture. So this is really where the model shines. So again, translating that into your use cases, if you have a use case where one is you are dealing with large volume of inputs, large documents, long threads of information. This is perhaps the area where you should try out Jamba to see, is this now more viable for you to actually utilize in your application. On the throughput side, so we have measured that. This is actually done by artificial analysis, and you can actually go to the website and pull it up as well. But this is where we have measured the actual speed. So again, this model, in this case, Jamba 1.5 Mini, performs really well comparable to other models where now you get a much faster inference time. And again, looking back, this is all done on a very small instance, right? Small in terms of like large clusters of GPUs. So again, you get a very, very good performing model. If you have use cases that are real-time use cases, perhaps, that's a good use case for getting the responses fast, high-quality responses. We also took a look at latency. And the challenge with that is, as you send more and more data, that latency increases. So your overall capabilities of sending more and more requests is always diminishing with the more information you send. And you can see that, so Jamba is that magenta line at the very top. It decreases less than the traditional transformer architecture. And that's kind of the area that we essentially see our customers exercise. As they send more and more information, larger and larger prompts, we're still maintaining the same efficiency of this model. So last thing I wanted to mention, we didn't sacrifice quality. So we want to make sure that, as you obviously exercise these use cases, it's impossible to kind of in a commercial terms to say, you know what, I'm just going to forget the quality. I'm going to focus purely on cost and speed. So by mixing in obviously the architecture from transformers, we retain the transformer type of quality, and we have exercised some of the academic benchmarks, and all of those are available both through our paper and on the website. And you can kind of compare where Jamba Mini and Large sit against other models. So as you're considering utilizing model for your use case, you have some additional input data. And again, each benchmark is very specific to a use case. So I would love to have a discussion maybe afterwards if your use case requires very specific testing. We have quite a few customers that we're helping with figuring out how well does our model perform in their specific use case. But we have quite a few data points we're happy to share, and I'll just give you a starting point for consideration. On the quality side, again, I want to stress that as much as you can test in the kind of academic environment the models, it's always a difference between kind of a synthetic test versus your actual environment and your application. And I would like to explore perhaps after the session kind of which areas maybe you have had challenges with before, and especially around large context size. So here on long context benchmarks, and this is available on GitHub as well. Again, wanted to showcase that as we are increasing the context size, we're maintaining relevant quality. And on quite a few models that we have worked with in the past, the challenge was that as you increase the context size, at some point, essentially it becomes unusable. So here's where you can actually see, and you can test it very quickly on Bedrock. With large context, the context is still usable. So if you've ever sent maybe in the past the model large document, and all of a sudden, like came back with either couldn't find the information or just you have a bunch of hallucinations. This is really the challenge that we have seen as well in the past. And that's where Jamba excels. You can send a large context to the model, and it performs really well with that. We have quite a few use cases, and I have some examples where customers really cannot divide these documents into sections, or dividing documents into sections or segments is very inefficient. Right, so this is the use case for just send one large data set. So let me talk a little bit about the real-world usage. And this is kind of a colleague of mine always refers to it as, you have to pick the right tool for the job. You probably don't want that massive Thor hammer for every single project. We have a very, very specific tool. Again, I'm kind of stressing low latency, really large context window, and efficiency as kind of the main trait. And really what we see that, kind of a prime example, long trails of social media messages, for example, right? And when you're analyzing large amounts of information, again, it's not always feasible to divide it into segments. When you divide into segments, one is you have some inefficiency because these segments now, they live separately. Perhaps you even have to run separate prompts on each of the segments, right? So running one prompt is much more efficient. Second thing is when you have things that are separate and you need to join information across them, that may be challenging. Let's say you're summarizing, and you're summarizing these, the main topics discussed, or you're summarizing this information. As soon as you divide something into segments, now you have to have some mechanism bringing it back together. So perhaps you're summarizing segments and then summarizing the summaries, or the mechanism to bring it back together. Hence, again, having one large context window helps you with creating that cohesive message at the end when you produce the output. Another example, and this is very common, is essentially in the finance industry, in the banking. We see a lot of guardrails that have to be executed very quickly. So this is where that optimization that we have introduced for performance comes in play, where you have to check every single input for specific guardrail, and it has to happen very, very quickly because this happens alongside maybe other prompts that you're executing. Also, really, when you're talking about cost consideration on sending really, really large data sets, you can run, again, a single GPU with a sizable input size. This is 140,000 tokens. To achieve the full 256, you need multiple GPUs. But again, 140,000 is a quite sizable amount when you consider large documents. Often they will fit into that maximum, and you can run it on a single GPU. So that has been quite a bit of a challenge because obviously GPUs are scarce resources, and having the capability to run that size on a single GPU has proven to be very beneficial for a lot of customers because before that they couldn't essentially unlock some of these quality queries. And last example I want to mention, really when you need a very consistent output. This goes back to a lot of medical use cases. We have customers that are sending large amounts of think of it journal information or large segments from their medical records and require always very reliable output. In our recent model, we are very much focused on achieving that minimal hallucination output. We have shown that for the RAG use cases, we are erroring out on the side of cautions for a lot of use cases, and you can essentially do it with the prompt as well. You can essentially enforce it with the prompt where you say, what, just if you really can't find it, just say I couldn't find it. Don't make up new information. And that has proven very useful in medical use case. For example, you don't want to essentially add additional content if you can't find it. It's better to just say, just just say you couldn't find it in the source information. So our model provides very reliable output. And then ultimately, you want to make sure that as you're utilizing these large use cases, you take a look at the overall cost, balance of speed, you take a look at the actual quality output. And we've been working with customers a lot with the challenge they had in the past, where they had to introduce new technologies because either the context size wouldn't fit or the performance wasn't there. So it's actually a mechanism for us to also revisit all use cases, where even ourselves, I would say 8-10 months ago, we had to add additional layers of essentially application to deal with these deficiencies. And nowadays, we're looking back at these use cases and saying, we can just do it with a single prompt. So it simplifies a lot of use cases. It also makes them essentially feasible. So a couple of things to review. So again, this architecture heavily indexes on speed and memory, and maintains a quality that's comparable with other models. We want to make sure that's the forefront of our offering. And then also we're using unique pieces of multiple architectures, and this will evolve in time. I'm sure this picture will change. Maybe it won't be as funny, but it will change. We're always experimenting and figuring out what's the right model, what's the right architecture. We are seeing this is model version 1.5. Obviously, there'll be newer, better models, but we're seeing a lot of need for even larger context windows and even more quality, right? That's really where the customers are looking for. I want to send more and more data, and I still want to maintain my quality. I have a couple resources. So we have a white paper on the architecture. If you want to really dive deep and kind of understand how this Jamba model has been put together, this is a very worthwhile place to take a look at. We have a number of resources on GitHub. So if you're a developer or you need a starting point with actual code, we have notebooks and we have code samples with Bedrock, as well as just kind of standalone, where you can immediately just get started with your project. We have a team that helps you, essentially takes you to the initial stages of development, ideation through all the way to production implementation. So please connect with us and reach out. And really let me know what other resources maybe would be helpful. Sometimes the resources we create are based on our kind of experience that we see in the marketplace, but really would love to hear from everybody, like, what else should we create? What would help jumpstart your projects? Thank you so much for the attention and the time you took to review this architecture. I want to leave quite a little bit of time to really talk about your use cases. I will jumpstart the discussion. I brought a couple of giveaways. Because I only have 4, what I was thinking is I will ask a question. I will lead with some simple ones. And if someone will be willing to answer, I have a few of those giveaways. So I'll start with like a very, very basic one. What's our context, the actual prompt size? If anyone remembers. Oh, I see someone raise.
256K tokens.
Very good. Yeah. So perfect. Awesome. Thank you so much. Thank you. So our context size is 256. Again, if you go to Bedrock and you look at all the models, you can see right there the available context size. And if you have a use case where you're sending large amounts of data, especially you say I need to send the full document, this may fit into 256K. It really depends on the document, but we also have essentially a token estimator, so you can just kind of send that to a token estimator to figure it out, or just try it out. Sometimes I just go in and I actually send it because the result gives you how many tokens it's using, so that's another way to try it. All right, another question I have is, based on the unique architecture of Jamba, could someone name a unique component that we have introduced in Jamba? A unique component of an architecture. You saw that kind of funny picture.
A router?
Yeah, router. So in the mixture of experts, we have router. Perfect. Very good. We have also the mix of transformer and the state layers. Very good. Thank you. Awesome. All right. All right. Maybe a very, very kind of a easy one. Where are the places where you could utilize on AWS large language models? Name at least 2 places where you could deploy it and utilize it.
Bedrock and SageMaker.
Yeah, Bedrock, SageMaker, very good, awesome. All right. Thank you. So I have a last question. If someone would be willing to share, what is your current challenge, and kind of what do you see as kind of maybe a way to solve it? If you could shortly describe what are you struggling with in a GenAI space, and maybe we can talk about a little bit, brainstorm on solutions. Yeah?
Live translation that also covers like contextual elements, and doing that live is a bit of a challenge because you don't always have all the context to go, when they say the penny dropped, they were using this as an idiom as opposed to going, no, somebody actually dropped some money on the ground.
Awesome. Yeah, so you need more context besides just the input, kind of the raw input that you get. An example is when the penny drops, kind of get a lot more information on. So the prize is yours. I wanted to brainstorm for a second. Thank you so much for sharing that. I think that is a very common use case where we require more context than just the input. So think of it, a chatbot is a good example. Someone's asking a question, and the question needs more input, maybe last year of conversations, or just needs essentially kind of domain-specific input. And this is quite a common use case where you have a prompt, perhaps you organize it where you have the core of the question, and now you need to fill it up with context. And that context has to usually come from somewhere. In a lot of cases, it could be maybe like a RAG type of use case, right, where you maybe gather additional information. And this is kind of where we see, kind of a shameless plug here, where we see Jamba excels. This is often a dynamic context, especially as we go into the agentic kind of environment. This context has to be gathered ad hoc, because the user just asked a question. Now we have to figure out, okay, what other context do we need to gather to send into the prompt? And that usually, sometimes cannot be pre-trained, cannot be preconditioned. It's something that essentially is ad hoc. And we can gather this context, and in case of Jamba, now we have a 256K window to actually insert all of this content. So perhaps if it's a simple example, kind of maybe as a language example, but in a more complex use case where you may be asking about medical records, and you have years and years of medical records, you could actually collect all of those and ingest those at essentially inference time, and say, well, here's a question about this patient, and here's all of the records that we have for the last 5 years, and here's all of the even definitions. We have seen a use case where we had to provide definitions of some of the terms to augment the actual context window for the model to really understand, because the model wasn't trained on a lot of the medical terms. And that's where we have seen that large context window really helps, because you can essentially just collect all the information you need. This is a lot of information, but it fits into this large context window, and then send it all together. That's one idea I kind of immediately had. Anything maybe that you were thinking about, how to solve that problem with additional context?
The additional context is definitely one, and if you can do multimodal, then you could maybe put video or something so that you'd have enough context links to go, oh, they actually dropped something on the ground or what. And just being able to add tone or something like that in as well would also be helpful.
I love that, yeah, I love that. Yeah.
But mostly just the speed element for real time, and also to be able to kind of have multiple running, like this is as soon as possible, and here we're kind of going back and editing it. Once we get new data, we're updating it if necessary. Having that extra speed would be helpful there too.
That's awesome, yeah. So again, context is a key, and having that flexibility of adding additional context. I wish we had video as a modality. We don't, text only, but yeah, that's a very cool alternative to be able to provide more context. I love it. Good. I'll take a question maybe, or suggestion.
So I think, industry is obviously spending a lot of time on prompt side. But I do see, especially the cases you're talking about, you can take 1-year medical information and plug in, right? I see the prompt will have its limitations and restrictions. So if the vendors and model creators create the platform where you can fine-tune your model and get quickly with limited or less resources, that will be something. And it's also, if you think about the regulatory part, prompt has a loose end for regulatory observation. Fine-tuning models probably has a little bit easier process in that context. So are you guys thinking that should come up with a platform that will give the users to, generate or fine-tune model, come up with a smaller model and that kind of things?
Yes, I think you're describing the balance between when do you fine-tune versus maybe just do this dynamic prompt augmentation. And to your point, yes, I think we're moving to more and more tooling around making it easier, faster to fine-tune. Especially when you look at Bedrock and kind of how easy it is to now augment and customize models. But I think overall, you probably still will see both, because the challenge, there will be still a use case for more dynamic data that's still large in size, so it has to fit in a large prompt, in a large context window. So I think, yes, so ultimately, if you can predefine that data and you can structure it and then kind of incur the cost, upfront cost, you get to reap the benefit immediately at the inference time, and it's a smaller, faster, maybe performance. The challenges of all the use cases will probably still be out there that will require dynamic input at the inference time, and still will be a lot of that input. It won't be really feasible to do that pre-training ahead of time. So I think both, but yeah, it's a guess probably, right? Because if we get really good and really fast at fine-tuning, that's another way to do it, right? Just have to get really fast at it. Yeah.
And also, I think it makes it easier for you have to remember, for the enterprise to publish this model, they need to go through a audit and regulatory observations, right? So if prompt engineering has that challenge, fine-tuning probably is a little easier. That's another motivation for.
It feels more stable, right, and controlled maybe, right? So you have to apply some additional guardrails on your dynamic input. I agree. Yes, so there's a little bit of trade-off. Yeah. Good.
So there's one question there. 1 second.
Thank you. You mentioned as one of the use cases for Jamba,
yes, sir.
guardrails for chatbots for banks. So basically, we need to add guardrails for every single chat,
yes.
Input and output. Can you elaborate on that one? How much delay basically we are talking that Jamba adds or drops?
Yeah. So delay depends on the amount of data you send. So essentially the prompt size. That's really where the delay comes in. You will see a difference between Jamba Large and Jamba Mini. So if you can achieve the quality you need with Jamba Mini, it will give you that additional speed efficiency improvement. And then the question is really what's the size of that input? Because the cost is, the larger the input, the more you have to evaluate, and the larger the output, really that's probably the more expensive side of the equation. If your guardrails are maybe, interacting on a very small, section of data, and the output is yes and no, or something very, very, very minimal, I don't have an actual use case performance metrics, but it should be somewhere, this is a second or sub-second type of performance. So it should fit into real-time type of a chat situation where you have interaction that's live, that shouldn't incur additional long delay, multi-second delays. But I'll have to kind of preface that of it really depends what's the amount of data that you send in. We'd love to maybe chat afterwards to see kind of how much data were you thinking about and kind of solutions for that. Yeah. So for those long, so just kind of maybe ideate for those long use cases, we'll look for either some parallelization processes, some way of dividing it into smaller parts. But yeah, the length of prompt will affect the speed essentially. Yeah.
So one more question. First of all, this seems like a breakthrough when it comes to practical applications. When you have best of both worlds, both high throughput of mixture of experts architecture, but also low memory footprint because, MOE models are super fast, but usually they require lots of memory. But there's another practical method of quantization, of course, and with MOE, usually there is a performance degradation, which is more pronounced. So my question with Mamba and state space models, is the performance degradation when it comes to quantizing to, for example, 4 bits, is it less pronounced or more pronounced than with transformers and compared to non-MOE architectures as well? Thank you very much.
Thank you. So the question is, right, is there degradation when we go to like a 4-bit quantization? Actually, I don't know the answer. I'll take it as a follow-up question. But we do have on Hugging Face, you can see we have a specific type of quantization that's optimized to deploy on a limited hardware like A100, single A100 GPU. I don't know the details, but we have actually developed a specific, you can tune that parameter specific way to make it more optimal. For it's not 4, it's I believe it's 8 and 6. So it's 8 and 16, and we have essentially, as I understood it, it's a custom quantization. But I'll actually follow up on that. I don't know the answer.
Okay, thank you.
Sure, thank you.
I've got a next question for you. So this is more of a hand-waving, less technical, but kind of puts you in the hot spot that I think our first speaker was saying it's difficult to avoid future predictions. Where do you see context length being, a year from now or 2 years from now? And is it these sort of model improvements that you're describing driving it, or is it more of like hardware? I know Gemini claims it's 2 million context length. What are your predictions on that?
Yeah, so I think it's all of those things where we will see hardware improvements, like very specialized hardware for architecture, like what we're seeing now with transformers. Perhaps we'll grow into that with Mamba as well. And definitely models are going to improve and they're going to innovate. So this is from a paper from last year. We are here today. So, like in all honesty, I'm amazed how fast we're making progress. And my bet would be that we probably another architecture by the end of this year that will spur another family of models that will be even more efficient. I think in general the industry does have use cases with larger context windows, and that helps in a number of things. It helps with efficiencies when we don't have to divide things into chunks, and it helps with comprehension. So there are use cases that we'll just see larger and larger context windows. I don't know what's really kind of feasible as far as kind of commercially what's the right kind of a size to go beyond 256. But I do see use cases already where 256 is already constraining. So kind of my feel is by next year, it will be much larger, and again, it will help us dive into these use cases that today they're just not feasible commercially. Yeah, good question. I wish I knew. Good. Well, thank you so much, everyone. One more question, please. Go ahead.
Yeah, so great presentation. It was really, exploring to know about current, context model which is going on. I have a question regarding data analysis. Like if you mentioned some real world examples where you have data from, medical, financial institute. So I was recently learning about LLMs and AI, and also tried one web application to do exploratory data analysis. So how does this model can handle, even though there is a constraint on the context size, so if there is a financial data, many number of tuples and records are there. So is Jamba is that capable of running on it, and how it will be with respect to latency and like?
Yeah, so the actual content that ingested is usually expected to be formatted in some way. So if we're talking about just formatting of financial information, if there are tables or other types of structures, they have to be formatted to something that the model understands. We have spent quite a bit of time on understanding tables, but there are so many variations and so many ways of interpreting a table. I've seen many mechanisms of converting that kind of formatting. But in general, yes, the model works well with financial information, especially the part where you need a reliable output without hallucinations. But I would love to hear about kind of what type of inputs you have, and kind of maybe brainstorm on how to make it fit into into the input.
Like anything like structured or unstructured data, you can like, especially like if you specifically on bank records, so you can have a tables, or customer records, like the transaction records, that kind of data I'm talking about.
So just my personal experience, I've been successful with just ingesting well-formatted textual table representation. In some cases, depending on the complexity, I may have to augment it in some way, so to change the structure. But yeah, I would love to maybe talk about an example and we can kind of ideate. But it works. What I was just is to try it out. Essentially, try it out, especially on Bedrock. It's so easy. And see, does the model understand my table structure? Do I need to add additional metadata or restructure it? Yeah.
Thank you.
Thank you. Thank you so much, everyone. Really appreciate you taking your time and looking forward to the rest of the session. Cool.
Thank you so much, Sebastian.
Thank you so much, Mike.
And I just want to point out that I was on the stage just a moment ago saying how the models haven't changed in ages, and now you've just seen how I'm full of rubbish. Absolutely, AI21 Labs is pushing forward with Jamba and producing novel architectures. So please show your appreciation for Sebastian one more time. Thank you very much.
Thank you, Mike. Thank you, everyone.
And we are good for about 15 minutes, ever so slightly less, and we'll be back here with Applied Science from AWS. So don't go anywhere, but also go somewhere just for the next couple of minutes. Okay, thank you.